Hi, so as Seamus was saying, my name is Alex Perrier. I work at Berklee Online. It's the online extension of the Berklee College of Music in Boston. And I'm also a data science contributor to ODSC, who organized this great meetup tonight. And I'm going to be talking about large data with scikit-learn. Just for me to understand, how many of you just use scikit-learn regularly? Okay, so not everybody. Good. So just brief plan of the talk. What is large data? What are we talking when we're talking about large data? What is out of core? There's a lot of terminology around that. Out of core, streaming, online, mini batch. So I'll try to give some insight on that. Talk about a few algorithms, mostly stochastic gradient descent and mini batch k-means. Implementation in scikit-learn, and some example on some rather large data sets. So, what is large data? Large data, it's simple. It's really the data that's not going to fit into the main memory of your computer in your RAM. So for this old machine, it's after a few gigabytes, the computer just starts to be so slow that it's not workable. And the idea here is to move from these several gigs of in memory to hundreds of gigs of data on disk. So you're really expanding the processing capability of your models and your code and everything. And here we're talking about just large data on a single cluster, on a single machine. There's no cluster involved. It's not Hadoop. It's not big data. It's not Spark on clusters. Well, I'm talking about scikit-learn, but there's plenty of other options out there. You have platforms like Dado GraphLab Create, H2O. I haven't tried them, so I'm just mentioning them. You can buy, rent memory optimized AWS instances for not so much money. PySpark, GenSim is a great Python library for text processing, and of course R has many streaming packages also. So, talking about the terminology, one thing that really confused me when I started looking at that is there's many different terms to talk about it. So these are not definitions; it's just things I found on the web. I looked at forums, and this is more to illustrate the underlying concept of the different terms. So we have out of core, external memory. It just means that the algorithm is able to get data from disks instead of in memory. So of course it's slower, 10 to 100 times slower. Then we have offline algorithms who are that's what you use in normal scikit-learn training. So all the data is available from the start. Online streaming and mini batch, it's going to be serialized. And online means that the notion that you act on new data right away. Whereas with streaming, you can bufferize the data, act on it, make several passes. And with streaming, there's also a notion that old data is less important than new one. So this bit of different things. And then mini batch, what we're talking about today, is really you serialize the data, but it's blocks and chunks of data in series. Just a brief recap on the API in scikit-learn, which most of you must know. What's really great with scikit-learn is this very coherent and elegant and simple API for all the models and transformations. So you train your models on the fit method. You use the predict method to predict data, on your test set or on new data, and you use the score method on any of these models and models to assess the performance of your model. And that's very universal. In fact, in scikit-learn, the only thing that is a model, that is a class in Python, are these models and transformation, which makes it very universal. And so how will scikit-learn deal with out of core? The idea is really, as I said before, to split the data in blocks and to load each block in sequence and to train the model adaptively on each block. And then you have convergence and it works. And so scikit-learn does that in a very easy way. You just have to use the partial fit method instead of the fit method that we just saw. and in fact, you know, when I was preparing this talk, I thought, okay, what else am I going to talk about? Because that's all there is to it. Basically, use the partial fit instead of the fit. But there's other things to talk about. So one thing to be aware of when you're dealing with classification, you need to be able to, you need to give the model all the classes that are going to be dealt with, all the target classes. Otherwise, the model won't know how to deal with a new class that it hasn't seen before. So that's one thing. And so just a bit of code. So it's very easy in scikit-learn, but you still have to be able to present this data to the model. So this code is absolutely not working, and it's something I simplified from one of my code. So you have to create what's called a generator that will read the data on the disk, and that will streamingly, you know, present the data through this kind of method to the model. So you define these two functions, and for all your iterations, each block, you will get the training data, the block of training data, and then fit that to the classifier or the model. So don't use that code. There's plenty of other better codes online for generators in Python. So what kind of algorithms are we talking about? Sorry, just there's not so many. So not all the models in scikit-learn respond to this partial fit method. Basically, you have two main families for regression and classification. For regression classification, you have the stochastic gradient, and I call that a family because when you look at the way you update the model iteratively, it's the same concept with the two other models that are available, which is passive-aggressive and perceptron. Perceptron is just for classification. Then for classification, you have naive Bayes also, a multinomial or Bernoulli. And then for clustering and decomposition, and decomposition, you have mini-batch k-means, which is a mini-batch version of the k-means algorithm, and dictionary learning in PCA. So you don't have SVM, you don't have random forest. There are many other models out there that are not in scikit-learn with an online mini-batch version. Random forest exists as an online version. It's called Mondian forest. There's some easy to find. So yeah, I would just like to focus on the stochastic gradient part of it. So stochastic gradient in history, it comes from signal processing and linear filtering. So you have, let me play again with the mic. You have an input signal, you have a filter, you have an output of the filter, and this output is supposed to estimate, to be an estimation of the real signal here. Okay, and that's a convolution. So this has a very analytical solution, which is the optimal weight, and that's probably things you've seen already. Is the inverse of the correlation matrix of the input signal, and multiplied by the correlation matrix of the input signal and the y. And this has, so if you want to calculate that analytically, the computation cost is very high because it's if you have n samples, it's in n to the cube. So it's absolutely not practical to do that. So the gradient descent algorithm, which is deterministic, will recursively update the weight of the filter of the model with the gradient with the gradient. Okay, so that's the basis. So since that was too complex to calculate, what we had after that was the stochastic gradient descent, which is also called this mean square in signal processing literature. And what you do is you approximate the gradient with just one sample. So every time you have a new sample, you update the filter. This is great. This is you solve the computational problem, but you haven't. But then you have very slow convergence, and also since your approximation of the gradient is very, very poor, you have a lot of oscillation. So the efficiency of it is not that great. And just to note, that works because this term in the mean will be equivalent to will equal the real gradient, based on, of course, if your input is IID independent and analytically distributed. So that works, but this is not so great. So then we have the idea of estimating gradient with just taking a block of samples instead of just one sample, and that gives you what's implemented in scikit-learn, which is the mini-batch stochastic gradient descent algorithm, okay, which is also block elements. So you have far less gradient noise estimation, much better convergence, and it's still very, very optimizable, because if you choose your block size, in a smart way, as a power of 2 or something like that, you have a lot of matrix optimization available for you. So computationally speaking, it's pretty neat. It works well. As I was saying before, one other thing. So why do we have only these algorithms in scikit-learn that have this partial fit method? It's because when you look at the passive-regressive and perceptron, it's the same idea of iteratively adapting the filter. The model, sorry. It's just the way you adapt it. So for gradient descent, the loss function, so you change the loss function, and then the gradient. So the loss function is the mean square error. For passive-aggressive, it's something else called hinge loss. And for the perceptron, it's just adapting with +1 or -1 in the case of binary classification. So that's why it's basically the same idea of batching the data for these three algorithms. For k-means, so k-means, what I found is that the seminal paper seems to be from this Scully person from Google in 2010, which is a bit, I'm wondering if that's right, because, k-means has been around for 40 years, 30 years, 40 years, so I'm wondering, there's probably other people who've thought about doing an update block by block before this Mr. Scully, I forgot his first name. So anyway, so the idea is that for each mini batch of data, you do two passes. The first pass will look at all the samples in the batch, and for each sample X, find the center Cx. Okay, so remember that. And then at the next pass, you update the Cx center with the new sample that you found that was assigned in the first pass to that center. And you make sure that you count for the number of samples that were already associated with the center. That's the cardinality of the thing. So taken straight out of this paper that I just shown, here we have in blue we have the mini-batch k-means, which converges much faster than the normal k-means. And this is a stochastic gradient k-means, and I haven't looked at it. But basically, in the end, what we have is it's much faster. We obtain the same convergence level with mini-batch k-means. So that's good. That's right. Few things to know when you're doing mini-batch learning is that in classification you need to be it's important to give on each mini-batch a well-balanced mini-batch with respect to different classes. Because if you have one batch that's super imbalanced, then the model will be confused basically, and you will also. Then there are other considerations for these algorithms, perceptron, passive-aggressive, and SGD. They put different emphasis of samples over time with some decay over some old samples. But for me, the main question is, okay, how do you choose the batch size, and how does that influence the model and your results? Okay. You would think that the bigger the better in terms of, as long as you're not impacting your memory of your machine, having a bigger batch size would have a better estimation of the gradient, so that would be great. And what you have is really a balance between the time efficiency of training with small batch, and that's opposite. This is large batch and this is small batch, sorry. And versus the noisiness of the gradient estimate. So if you have a small batch, you have more noise, etc. But in fact, in certain cases, on certain data sets, having some noise is interesting because it will get you out of the local minima. If you have many local minimas, if you have something that is a bit noisy, you won't fall into the trap of the local minima. Okay? It's as if it's the same idea in a way of noise being a good thing, as in when you're ensembling weak learners, you know, like in the AdaBoost, you have random forests that are, or a random forest, you have a decision tree that are just one layer deep, so it's not great, but when you add them, you're getting better convergence. So noise is not always bad. So in practice, what you want is to have moderate mini batches size and a decaying learning rate, but that's the mu in the update of the gradient. That's another subject. Okay, so now 2 examples, the fun part. So scikit-learn has amazing code examples. So I took one of them on k-means, mini-batch k-means applied to the Reuters data set. And I ran it with simply different batch size, 100, 500, 2000, okay, and looked at what was happening. So here we have, yeah, it's pretty visible. Okay, so here we have 100, 500, and 2000. So, and the blue one, the blue line, which stands out, is the multinomial naive Bayes. Okay? So we see right away that the multinomial naive Bayes is very stable. It's not really converging very fast. It's very slow, but it's far more stable than these, these other 3 algorithms, which are, if we look at it more closely, which are perceptron and the passive-aggressive and the SGD. And even the perceptron really doesn't work well. It crashes all the time. It's every new batch. So it's very noisy. Yeah. And when you look at 500, you see that there's some smoothing effect, but the multinomial naive Bayes doesn't converge faster or anything like that. What's interesting also is to look at the training time. So also for 100, 500, 2000 for the mini-batch k-means on the same dataset, Reuters. Here you have multinomial naive Bayes, you have the 3 other ones, SGD, passive-aggressive, and perceptron. And this is the time used for vectorization of the text. When you do TF-DIF, the hashing trick, when you move your text from text to vector for numbers. And you see that increasing the batch size will decrease the training time of the algorithms, but of course, vectorization is still pretty high. Yes.
Are we allowed to ask questions?
Oh, please. Of
course,
yeah.
A quick question. Do you have an understanding of why the accuracy jumps crazy like that with each new batch? Is that so? It's just using.
Yeah, the thing here.
Learning. I mean, it drops to 0 sometimes, right? Oh, sorry.
Yeah, I think the perceptron is. That's really for the perceptron, and I think the perceptron in that dataset is absolutely not adapted. I guess if I had taken the perceptron out, the other ones are oscillating, but not that much. I mean, this is really, and why they're oscillating, I don't know.
I didn't realize the scale is 80%.
Yeah, sorry, the scale is not, 80%, going to 0. But in fact, what I had done before is that before running the simulation on the Reuters with scikit-learn code, what I had done, I was in that competition on the Kaggle competition that closed a few months ago, and the competition consisted in predicting whether an HTML page had native ads, so ads that didn't come from outside servers, but was really embedded in the same code. So we were given 30,000 HTML pages for a total of 36 gigabytes, so it's getting large. And there was a lot of pre-processing, feature extraction, vectorization, hashing trick, all that. In the end, I took 10,000 pages for the training set and 4,000 pages for the test set. Okay, and this one is just an illustration on my machine of the RAM. So the blue line is in memory without batch, so of course it explodes. And the other one is for different size of batch, 10, 20, 100. And we see that the memory consumption stays very low and nice. Okay, so what was interesting is that I saw exactly the same behavior of the three different algorithms with a totally different data set and my code, which is far less great than scikit-learn code. So we have the multineural, which has problems at the beginning, but then it converges pretty stably and even reaches higher accuracy. The accuracy is not that great, but it was more a proof of concept than the computation itself. And then the other one, the perceptron here, that confirms what we are seeing on the other data set. It just doesn't converge at all. There's nothing. It stays around, 70%. And the other two are very noisy. And that's for the accuracy. So I looked also at recall. I don't have the slide here. Recall, the other two, the three algorithms were just basically white noise. It was extremely noisy and going back and forth with each iteration. Another thing I looked at is so changing the batch size for the knife bias algorithm for accuracy and recall. And we see that the batch size goes from 10, 100, 500. And the algorithm converges much faster as you increase the batch size. In fact, for 10, it doesn't even converge. Whereas for the recall, there was something interesting in terms of the algorithm would reach a very, very high score, and then there was a slow decay after that. So weird things happening. Okay, so as I was saying earlier, in this one, what's killing us all the time, and what's killed me in the kind of competition was really the time it took to process the data. And so I think we were out of time, and I didn't have time to present something on that. But really, what I wanted to pitch in for this thing, which is called Dask, which is a new library, and that basically Dask is a library that will allow you to do all the data munging and all the data processing. It's released by Continuum.io, who released, they're behind Conda. It's super easy to install. Pip install Dask. There's no JavaScript machine like Spark, which is a plus. It's very easy to use because it really copies the NumPy interface. So you get to speed very quickly, very little code changes, and it uses what they call blocked algorithms. So each operation is decomposed in a series of parallel operations. There's a great video from this guy, Matthew Lachlan, by data. It's on YouTube. The link goes to YouTube, where he shows how each operation gets divided into several parallel operations, and you get a lot of boost in speed on the data munging part. So that's the other brick in the large data processing. And looking at what's being said in scikit-learn right now, they are talking about using Dask, maybe Blaze Dask and that kind of thing to power to go underneath in scikit-learn in future versions to speed up the data munging part. And that's it. Thank you. So questions? I have to turn that off.